The title of this lecture is Fast File System. This is the disk layout of the first Unix file system. At the beginning of the file system partition, there is a super block, and then there is inodes, and so we call it inode table, and then there's data blocks. So this is the file system layout of the first Unix file system. At that time, it was a great invention. So it is simple, and it supports basic abstractions, and it's easy to use. However, they soon found out that there was a serious performance problem. So they proposed a new file system called Fast File System. Fast File System, called FFS. So in this chapter, we're going to study how the first Unix file system can improve. The first one is the fragmented file. Unix file system treated the disk as a random access memory. So let's consider the following layouts. There are 4 files, A, B, C, and D. And each file consists of 2 blocks. File A consists of A1 and A2. And likewise, file B consists of B1 and B2. And file C consists of C1 and C2. And file D consists of D1 and D2. So in laying out those blocks, it is very important that data blocks associated with a same file are placed in consecutive manner, in consecutive sections. However, let's consider the situation file B and file D is deleted. And then a file system create a new file, file E, and it has 4 blocks. And then the only way to place 4 blocks associated file E is to use the empty spots that has been used by file B and D. So the 4 blocks for file E, for E1 and E2, and E3 and E4 consists of 2 distinct consecutive segments. So the data blocks are spread across the file system partition. We call it as a fragmented file. Let me try it again. Fragmented. The problem of a fragmented file is disk seek. If the data blocks associated with a single file is fragmented over the disk surface, then it causes lots of disk seeks. So they have come up with a new file system called Fast File System. It is developed by a group of people at Berkeley, and the basic essential feature of the Fast File System is that all the features in the Fast File System is designed to be disk aware. And they use the same API with the file system. FFS uses open, read, write, and everything. However, they have changed the internal behavior of the file system. So they have come up with the very important concept of cylinder group. FFS divides the disk into a bunch of groups. Each of the group is called cylinder group. And the concept of cylinder group is still being used in the modern Linux file systems such as ext4. These groups are used to improve disk seek performance. That's to improve the seek performance. Let me explain how it works. When a file system partition consists of a set of cylinder group, the file system places 2 files in the same group. So that if 2 files belong to the same directory, then file system tries to place those 2 files at the same file group. So accessing one after the other will not be long sec across the disk. And also FFS needs to allocate the files and directories within each of these groups. So, in the previous chapter, we saw that a single file system partition requires a bunch of metadata, such as inode bitmap, data block bitmap, and stuff like that. In fast file system, these data structures are defined for each cylindrical group. And at the beginning of each group, it maintains a copy of the superblock for reliability reason. And then each block group or cylinder group contains inode bitmap and data bitmap to keep track of inode and data block. And then there comes inode and data block. So this is the layout of single cylinder group. And then a file system partition consists of a number of cylinder group, stuff like that. Okay, so this is physical layout of how the cylinder group look like. Disk consists of a surface, a plateau, and plateau has a surface. And so if you fix the disk arm and rotate the plateau, then it'll form a track. And then if there are multiple plateau, for example, modern hard disk drive may contain 2 to 3 plateau. And for each plateau, there are 2 surfaces on the upside and downside, upside and downside. So if you fix the position of the disk head and rotate the platters, then the set of tracks form a cylinder. So a cylinder group is a set of n consecutive cylinders. Okay. So this one is called a single track. And there's another track. And there's another track. So if you collect all the tracks in the same cylindrical position at each plateau, then that will form a cylinder. And a cylinder group is a set of consecutive cylinders. That's what we call cylinder group. So how do we exploit the cylindrical group in hard disk drive? The philosophy is keep the related stuff together. Why? To reduce the seek time. And so placement of directories. Find the cylinder group with a low number of allocated directories and high number of free inodes, and then place the new directories there. And then there, the directory block and the associated inode are placed in the same cylindrical group. Why? So this is to minimize the distance between inode and directory block. So if you consider the first Unix file system here, at the beginning of the file system partition, there is superblock and there is inode tables and then data blocks. So directory block may be located at the very end of the file system partition, and the associated inode may be placed at the beginning of the file system partition. This distance is very large, which incurs a long seek, because if we consider like open operation of a directory, and then you have to access the inode and then associate data blocks, and the seek distance is going to be very large in this situation. However, if we consider a cylindrical group in FFS, then it partitions entire file system partition into a number of cylindrical group, and each cylindrical group has inode table and the data blocks. So in this case, the inode for a directory may stay relatively closer to its directory data block. So let's say this is data block for directory, data block for directory, and then this is the inode for the directory. Then distance between the two is relatively smaller than the distance between the two in the non-cylindrical group file system partition. And also, when you place the files, we can allocate the data blocks of a file within the same group as its inode. So, and also it places all files in the group as their directory. So there are many advantages in exploring the concept of a cylinder group. Let me provide an example. Let's say there are 10 groups. And then each group has 10 inodes and 10 data blocks. There are 3 directories, slash, slash A, and slash B. And there are 4 files, slash A, slash C, slash A, slash D, slash A, slash E, and slash B, slash F. So there are 4 files. And let's examine how these 4 files, how these files are located and placed based upon a number of cylinder group. So in the first group, the root directory, in group 0, an inode and the data block for root slash file system are all located. So there are root directory inode and then data blocks for the root directory. And then under the root, there are 2 files, A and B, in both the directories. And in group 1, inodes for file A, C, D, and E is allocated. And then also the data blocks for A, C, D, E are also located. And there are 6 free inodes here. And then in group 2, there are inodes for B and F are located. And the file B has 1 data block and file F has 2 data blocks. And there are 8 free inodes and 7 free data blocks. So for each cylinder group, inode and the associated data blocks are clustered together. A fast file system has its own specific allocation policy. Data blocks of each file are near each file's inode, and more important, the files in the same directory are near one another. For example, here slash A has a directory CD. Directory A has a file C and file D. So they place it in the same cylindrical group. In the same manner, file F, which is under the directory B, so they are placed at a separate cylindrical group. However, if we do not apply fast file system allocation policy, then all the files and directories are placed in round-robin manner. So without fast file system policy, it simply spread directories and files across the cylinder groups. This data shows the ground reason for why FFS come up with such design. A seer trace is the trace obtained from the file system. It shows the file accesses and it shows path difference. Path difference is how far up the directory tree you have to travel to find the common ancestor of the 2 files. So in seer trace, it computes the path difference between the consecutive accessor to a file. Okay, so if there are 2 files on the bar slash A slash B and slash A slash C, then file B and file C, it meets the same parent directory when they go up 1 path up. So the path difference between those 2 are just 1. So how far up the directory tree you have to travel to find the common ancestor of the 2 files? There are 2 cases. First one is random. Then second one is what is observed from the trace. This is the path difference obtained from the trace. As you can see, the path difference is much smaller in the actually observed trace. So that is the reason why the FFS file system places the files on the same directory together in the same cylindrical group. Let's consider the case where a file size is very large. If we do not consider large file, then in this case, if a single file consists of 10 blocks and they are planning to place that files in a group G2, then G2 will be occupied by all the blocks from a single file. So any of the new directory entries created in the G2, the associated data blocks will be placed in the other cylindrical group. To handle those kind of large file problem, FFS limits the number of data blocks that can be placed on a single cylinder. For example, in this example, a file can place only 2 blocks for each cylindrical group. 0, 1 here, 2, 3 here, 4, 5 here, 6, 7 here, and 8, 9 here. Okay. So this is to avoid that a single file fully consume entire free blocks in a single cylindrical group. So how big do chunks have to be? In FFS, it places the first 12 direct blocks in the same cylindrical group. And then in direct block, all blocks it places in a different group. So that is the policy of block placement in fast file system. And there are a few other things about FFS. There is internal fragmentation, and it also handles subblocks efficiently. In file system, the minimum block size is 4 kilobyte. So even though a file system contains only 512 byte, in the Unix file system, it allocates entire 4 kilobytes and use only 512 bytes out of 4 kilobytes. It's a wastage of space. To avoid that, in fast file system, it allows subblock file. And then it comes up with the track buffer, and it allows very long file names, which is 256, and it comes up with an idea of symbolic link. So there are a lot of tiny little inventions in fast file system. So fast file system finds the problem of file management in one of the most important issues within an operating system, and it makes file system faster based upon the physical characteristics of the disk. Many of the existing file systems still inherit the various characteristics of fast file system, including ext3, ext2, and ext4.